We're going to look today at calculations involving the Avogadro number. The first thing we need to remind ourselves is that Na is the symbol that we use to represent the Avogadro number, and it's a constant. It always has this value, 6.022 times 10 to the 23. What that means is if we were to have 1 mole of any substance, it would have that many particles in it. All we're really going to look at today is how we use it in calculations. We don't really need to understand too much about it, but it is a constant. If we ever see Na, that's the value that we will use. So our first calculations involving this are going to be to calculate the number of atoms or the number of molecules in a certain quantity of a substance. So we're going to our question that we're going to work through is to calculate the number of atoms in 46 grams of sodium. And remember that sodium has the symbol Na. So we're going to need to use an equation for that. The equation we need is the number of atoms equals the number of moles multiplied by Na, by this Avogadro constant here. We know what Na is. Na is our constant. We don't know the number of moles from this question. We're just given the mass of it. So the first thing we're going to have to do is to calculate the number of moles. So the moles of Na, which is this one here, is going to be equal to the mass of it divided by its relative atomic mass. And remember that symbol there, capital A with a small subscript r, is the symbol for relative atomic mass. Now I've chosen Na here just to emphasize that actually we use two very similar looking symbols. Na, the element, is a capital N with a small a after it. The symbol for the Avogadro constant is a capital N with a subscript capital A. So there is a difference between those. Na there is for the element, that there is the Avogadro constant. So we've done this part. So the moles of Na is going to be equal to its mass, which is 46 grams, divided by its AR, which is 23. Now that I could find from the periodic table. The relative atomic mass of Na is 23. That will give us an answer of 2 moles. So we've found the number of moles, which we can now put into our equation. I'm just going to write that equation out one more time, just to show what we're doing. So the number of atoms is equal to the moles multiplied by the Avogadro constant. Remember this time that's a different symbol to the symbol for the element. So let's substitute the numbers in. We've calculated the number of moles as 2. We know that the Avogadro constant is always 6.022 times 10 to the 23, which gives us a final answer of 1.204 times 10 to the 24 atoms. And that's in 2 grams of sodium. That's a huge number. That's a very, very big number, and that's what we would expect to see. It's always worth, at the end of one of these, is just checking in our heads, does that number make sense? And we would say yes, it does, because we know that atoms are very, very small. So if we've got an amount of sodium, we're going to have a huge number of atoms in it. Let's have a look at another example. We'll move through this one a bit quicker because we don't need to spend quite as much time on it. So we're going to calculate the number of atoms in 0.04 grams of the element helium. We're going to need our equation of number of atoms equals moles multiplied by the Avogadro constant. We will first of all need to calculate the number of moles. So the number of moles equals mass divided by the relative atomic mass, AR. So moles of helium equals 0.04 grams divided by 4. Where did I get 4 from? 4 is the relative atomic mass of helium. I would have found it from the periodic table. So that gives us an answer of 0.01 moles. Let's now write out the second part of our calculation. So the number of atoms equals moles multiplied by the Avogadro constant. We've calculated our number of moles as 0.01. The Avogadro constant is 6.022 times 10 to the 23, which gives us an answer of 6.022 times 10 to the 21. So let's have a look now if we were to do this with a molecule. So our question now is going to be to calculate, this is question 3, calculate the number of molecules in 11 grams of carbon dioxide. So we'll need our same equation again. Number of molecules in this case, is going to be equal to the number of moles multiplied by the Avogadro constant. We need to calculate our number of moles first of all. Moles equals mass divided by, and this time it's MR. So MR is the relative molecular mass. In our previous two examples, we were looking at just an element. So we were talking about its AR, its relative atomic mass. Now we need to be looking at its MR, relative molecular mass. So how do we calculate the the MR of carbon dioxide? Well, we know that carbon dioxide, a molecule of carbon dioxide has 1 carbon atom in it and 2 oxygen atoms in it. We would find from the periodic table that carbon has a relative atomic mass of 12 and oxygen has a relative atomic mass of 16. So 2 oxygens gives us 32. So all of that, the MR of carbon dioxide is 44. So we can put that into our equation. The mass of carbon dioxide is 11 grams divided by the MR that we've calculated, which is 44, and that gives us a moles of carbon dioxide as 0.25 or a quarter. So then let's put that into our equation. The number of molecules equals moles multiplied by the Avogadro constant. That is equal to 0.25 multiplied by 6.022 times 10 to the 23, which gives us an answer of 1.50 times 10 to the 23. So that's our calculations for calculating the number of particles. The thing we're going to look at now is how we use the Avogadro constant to calculate the mass of a single atom. So the mass of a single atom. Now remember that atoms are very, very small. We're expecting these to have a very, very small mass. The equation we need here is mass of an atom is equal to AR, which is the relative atomic mass, divided by Na, which is our Avogadro constant. Let's have a look at an example question. That'll be question 4 here. Calculate the mass of one atom of calcium. So mass of calcium equals AR, which is 40, and I would need to use the periodic table to find that, divided by 6.022 times 10 to the 23, gives us an answer of 6.64 times 10 to the minus 23 of a gram. That's very, very, very small. And again, that's what we would expect. One more example, question 5. We're going to do the mass of one atom of sodium, Na. So the mass of one atom of sodium is equal to the AR, which in this case is 23. I would find that on the periodic table, divided by 6.022 times 10 to the 23, gives us an answer of 3.82 times 10 to the minus 23. Again, a very, very small number. Thank you very much.